Here today I'm going to present on doping assessment of beryllium doped gallium arsenide and tellurium doped gallium arsenide antimonide nanowires. 3,5 semiconductor nanowires have significantly attracted researchers due to 1D architecture, quantum confinement effects, and a higher tolerance for strain mismatch that allow greater freedom in bandgap engineering of material systems in a variety of different nanowire architectures to meet the demands of next generation optoelectronic devices. Dopant incorporation in a well-controlled manner is essential to produce abrupt interfaces, to modulate work function, and to realize advanced devices in nanowire configuration successfully. Unfortunately, the thin film studies on dopant incorporations and carrier concentration cannot be directly translated to nanowires due to the doping's influence on the growth kinetics and different growth mechanisms along the axial and radial directions. Commonly used measurement techniques in thin films for the determination of carrier concentration, namely Hall effect, field effect transistor measurements, require highly sophisticated lithography steps. The uncertainty of the gate capacitance and contact resistance in the case of nanowire FET can further limit the accuracy of carrier mobility and the concentration values. In recent years, several characterization methods have evolved for the assessment of dopants in nanowires. These are secondary ion mass spectrometry, off-axis electron holography, and atom probe tomography, where all these techniques are found to be destructive. In this work, we evaluate the carrier concentration and incorporation of beryllium dopants in gallium arsenide nanowires and tellurium dopants in gallium arsenide antimonide nanowires grown using gallium-assisted molecular beam epitaxy with variation in beryllium cell temperatures from 750 degrees Celsius to 950 degrees Celsius and gallium telluride cell temperatures from 500 degrees Celsius to 570 degrees Celsius respectively, using conductive atomic force microscopy, scanning Kelvin probe microscopy, X-ray photoelectron spectroscopy, and ultraviolet photoelectron spectroscopy, as they do not involve any contact fabrications. Statistical analysis of all four measurement techniques have provided evidence for confirmation of incorporation of beryllium and tellurium in gallium arsenide and gallium arsenide antimonide nanowires. Hence, these surface analytical tools without contact fabrication are found to be a very successful and powerful tool for direct measurement of the dopant incorporation and doping levels in nanowires. The intrinsic beryllium doped and tellurium doped nanowires were grown in EPI 930 solid source MBE system with valved arsenic and antimony as the group 5 constituent cracker sources. On the left side, a CM image of the ensemble beryllium doped gallium arsenide nanowires grown at beryllium cell temperature of 950 degrees Celsius is shown, whereas on the right side, a CM image of tellurium doped gallium arsenide antimonide nanowires grown at gallium telluride cell temperature of 550 degrees Celsius is shown. Conductive atomic force microscopy, the intrinsic beryllium doped and tellurium doped nanowires were grown in an EPI. So here the electrical characteristics have been investigated using CEFM, a technique in which the electrical current passing through the tip and the sample is recorded. A current map of the surface of the sample at a given bias gives us a single slice of the conductivity of the sample. Current voltage spectra of the sample are measured using CAFM. Titanium iridium conductor tips with a tip radius of 25 nanometer has been used. It has to be noted that the tip radius should be lesser than the feature we are scanning for high spatial resolution. To illuminate the sample, a laser of the wavelength of 860 nanometer was used. Current mapping under a DC bias of 600 millivolt is done. Top contact is the AFM tip to the top of the sample, and bottom contact is the gold-coated contact connected to the silicon substrate. The top row shows the topography of an array of vertically aligned beryllium-doped gallium arsenide nanowires, while the bottom row shows the corresponding current mapping of the doped nanowires. From the current mapping, it is observed that the current density has improved for beryllium-doped gallium arsenide nanowires with the increase in beryllium cell temperature. In this, the left column depicts the topography of an array of vertically aligned tellurium-doped gallium arsenide antimonide nanowires, while the right column shows the corresponding current mapping of the doped nanowires. Here, N represents tellurium doping at the particular cell temperature. It is evident that the N550 sample is more conductive. The finite element method numerical solving technique was used to model nanowires with Schottky contact on one side and rectifying contact on the other side using COMSOL multiphysics simulation software for beryllium-doped gallium arsenide nanowire samples. From COMSOL multiphysics fitting, a statistical increase in the carrier concentration of beryllium-doped gallium arsenide at beryllium cell temperature of 750 degrees Celsius, 850 degrees Celsius, and 950 degrees Celsius is observed and are found to be 9 into 10 to the power 15 per centimeter cube, 7 into 10 to the power 17 per centimeter cube, and 5 into 10 to the power 18 per centimeter cube. This confirms an increase in doping of nanowires with increasing beryllium cell temperature. Here, an estimated carrier concentration of 7.1 into 10 to the power 17 per centimeter cube, 3 into 10 to the power 19 per centimeter cube, and 3 into 10 to the power 18 per centimeter cube are determined for the tellurium-doped gallium arsenide antimonide nanowires at gallium telluride cell temperature of 500 degrees Celsius, 550 degrees Celsius, and 570 degrees Celsius, respectively, from COMSOL multiphysics fitting. Along with COMSOL fitting, Hadaoni-Stratton fitting has also been carried out. This has been discussed in detail in our paper that has been published recently in Scientific Reports Journal. This graph shows that the values obtained from COMSOL and UPS concur very well, which will be discussed in the upcoming slides. Scanning Kelvin probe microscopy. SKPM scanning of the nanowire samples was carried out using lift mode, which uses 2 separate passes per scan line. The sample topography is measured in the first pass, while the surface potential is measured in the second pass. From these SKPM surface potential images, a decreased contact potential difference between the nanowire and gold surface can be observed in the beryllium-doped samples, which reflects increased work function with beryllium cell temperature, and vice versa for tellurium gallium arsenide antimonide nanowires. However, as the measurement is carried out at the room temperature, the biased voltage, probe tips, and also the presence of absorbent and surface states in the nanoscale regime have a significant effect on the surface potential measurement. Hence, quantitative analysis was not performed. Working of XPS. In XPS, the kinetic energy of the emitted electrons radiated with soft X-rays from the sample is analyzed. The result of the complete transfer of the X-ray energy to a core level electron is the emitted photoelectron. The working of UPS is similar to XPS but irradiated with a UV source. The work function of the material can be evaluated using UPS. XPS UPS measurements were performed with a thermo-escalab 250Xi using monochromated aluminum K alpha X-ray source and helium-1 photon source, respectively. The atomic forces of gallium over arsenic for beryllium-doped gallium arsenide and tellurium-doped gallium arsenide antimonide samples are found to be around 1. While antimony over arsenic for tellurium-doped gallium arsenide antimonide samples are found to be around 0.07. With increasing beryllium cell temperature for gallium arsenide nanowires, a shift in Fermi level towards the valence band provide evidence towards higher beryllium incretion with beryllium cell temperature of 950 degrees Celsius, having work function and carrier concentration of 5.6 electron volt and 6 into 10 to the power 18 per centimeter cube, respectively. The lowering of the work function manifested by a positive shift in the binding energy of the UPS spectra of tellurium-doped gallium arsenide antimonide nanowires grown at the gallium telluride cell temperature of 550 degrees Celsius revealed the sample to be heavily doped N-doped sample with a carrier concentration of 2.8 into 10 to the power 19 per centimeter cube. Conclusion, the values of carrier density from UPS concur very well with the values of carrier density determined from GaAsFM. The change in surface potential observed in doped nanowires in SKPM characterization also provided strong evidence of beryllium incorporation and tellurium incorporation. Hence, a combination of contactless methods where no fabrication of contacts being involved, such as GaAsFM, SKPM, XPS, and UPS, or other convenient techniques for the assessment of dopants and nanowires that are critical to band gap engineering design for the application of optoelectronic devices. References. Thank you.